So we got a little bit left to go here on the chapter we are currently lecturing in. We were talking about electron configuration last time. And so let's pick it up kind of from there. So remember, electron configuration basically gives the order at which the electrons fill the atom. And basically, as we talked about last time, there's a specific order, and it has to do with energy. And the electrons do go in lowest energy first. And then if they fill sort of that level up, then they go to the next lowest and the next lowest. And they really do continue filling until, you go from the lowest energy to really the highest energy, and they're out of electrons. And this again over here is the order at which electrons go into the atom. Again, we always start at the top here, and we basically zigzag back and forth. And as we talked about last time, pretty much if you know this or how to recreate this, which we talked about how to do the other day, I think as well, you really should be able to write any type of electron configuration that you need. Remembering as well that, again, s orbitals could only hold a maximum of 2 electrons. If you fill the p subshell, that's 6 electrons, d subshell, that's 10 electrons, and if you fill the f subshell, that is 14 electrons. We also talked sort of, how electrons go in with the arrows and stuff like that. Again, just sort of how they do fill sort of the orbitals. We did a number of electron configurations on this page here, at least the first 10 or so. I think we left off talking about calcium here, and a reminder that there is sort of a shorthand that is sometimes used for electron configuration. And for example, if we look at calcium's configuration, what is highlighted here in yellow is basically the same electron configuration as argon, which is a noble gas. So we put argon in sort of brackets, and then we continue on with the configuration. And again, it's sort of a shorthand way of doing electron configuration. Always, as we talked about last time, it should be a noble gas that goes into that bracket. And it's the noble gas that comes basically right before whatever element you may be writing the electron configuration for. Any questions on that stuff we talked about last time there? So again, if we looked at, for example, here, if we looked at, let's do, what do we want to do? Let's do, let's do sodium, for example, and sodium, which is 11, would be 1s2, 2s2, 2p6, and 3s1 would come next. Again, if we look at sodium, basically this part of sodium's configuration, and again, we can count the numbers up on top, that's 2, 4, and 6, give us 10, and that's the electron configuration for the noble gas of neon. And then we could continue on with the configuration. So again, this is what is referred to as noble gas configuration. And, you can use this as a shorthand if you want, or you can write it all out. Obviously, if it says don't do that, then obviously don't write it like that. Now, if we look at sort of our chart, a reminder that the way you can make it for yourself is pretty easy. Remember, S is start on the first energy level, P start on the second, D start on the third, and F start on the fourth. And after you kind of build that, you could just fill in all the numbers below and write the right letter. That would be helpful. 4S, 5S, 6S, 7S, 2P, 3P, 4P. I'm having trouble writing here today. 5P, 6P, 7P. There you go. 3D, 4D, 5D, 6D, and 4F, and 5F. So again, you could just kind of write all the numbers below it better than I just did there. We'll put the right letters there, help out a little bit, clean it up. And you really will have sort of the correct order here for yourself. And again, we kind of go this way. Now, if you follow this, this will pretty much give you the correct electron configuration for everybody. There are some exceptions, and 2 notable exceptions is chromium and copper, which are in the transition metal region. So if you look in the transition metal region, you'll see chromium and copper right there on top. Chromium is 24, copper is 29. So if we write the electron configuration for these guys, this would be 1s2, 2s2, 2p6, 3s2, 3p6. And if you follow this sort of zigzag after 3p, we would come down here to 4s2 and 3d4. And again, if you follow the zigzag like everything else, that is where you would end up. But it's been found experimentally that it has a different sort of electron configuration. And the difference actually happens here. Because those orbitals are really, really close to one another. In fact, the 4s and the 3d are really, really close to one another, that what ends up happening is an electron from the 4s actually goes up to the 3d, and the electron curve configuration for chromium, or the correct electron configuration, is it actually will end at the end with 4s1, 3d5. So one extra electron in the d orbital, one less electron in the s, and again, just been found experimentally to be more stable that way. Also puts basically maximizing the parallel spin in all those orbitals, so that's very helpful. Copper, kind of the same deal, 1s2, 2s2, 2p6, 3s2, 3p6, and now it actually has the same sort of exception, 4s1, 3d10. So that kind of fills it up. So for us, these are the two that you will be responsible for that are exceptions to following this sort of pathway over here. Just so you know, in reality, if you look at electron configuration on the periodic table below chromium and below copper, there's a lot of exceptions like this. In fact, there's PD on there, this, right around here. And that guy actually has no electrons in the s orbitals. They've all been basically promoted up to the d orbital. So there definitely is a lot of exceptions underneath those two on the periodic table. But in most chemistry classes, you're really just responsible for these two. So we'll stay with that. So the only kind of two sort of exceptions you'll be responsible for are these two right here. And again, chromium and copper. The exception is one extra electron in the d orbital, one less electron there in the s orbital. Now, any questions on that there?
Yeah, Professor Ifan.
Yeah.
I'm kind of a little mixed up about the orbitals, right?
Yeah.
You know how you wrote it from 1s down to 7s, vertical.
Yeah.
What's the difference between you putting it vertical and then doing it horizontal like this, like the chromium?
So I wrote, I think you're talking about this, yeah? This.
Yeah.
Here? Yeah, this is just the order. So that's just, if you kind of go just vertical, that is how you get the correct order of how the electrons go in. So remember, we always start up here and zigzag back and forth.
From left to right.
Yeah, so you start at the top and zigzag back. But if you needed to kind of create this for yourself, because it won't be given to you, you could create it for yourself really easily by going the first energy level. There's a 1s, the p's don't start till the second, the d's don't start to the third, and the f's don't start to the fourth. And then if you just fill in the numbers underneath each of these, that is how you can recreate what I just did up here in the correct order. And then you can do your zigzag, back and forth. So that's just a way to recreate sort of the order for you, relatively easy. Other questions?
Thank you.
Yep.
Oh, yeah.
Yeah. Oh, I'm sorry. I hit the wrong button. Unmute yourself. I'm sorry about that.
No, it's okay. Just real quick. So I know there's two ways to get the answer. The one that's on the bottom for the Na equals 11, what's it? Right here. Yeah, the bottom. What's the answer, or what's the way? What do you call that way?
That is sometimes referred to as like noble gas configuration, where you use a noble gas before it, kind of like a short.
We're gonna have to know that version, or does it matter? Because
if it doesn't say, like, just says give the electron configuration, you could write the top way or the bottom way. They're both perfectly fine. If it says don't use noble gas configuration, then you should write it like the top. So if there's no real specification, you technically could do either one. They're both correct. But most of the time, probably in this class, you would do the top way there with the
Can
one.
you show me one more time how you got the second?
Yeah.
How
Yeah,
did
so
you-
the second part of it comes from if we write the configuration there for sodium, which is 1s2, 2s2, 2p6, 3s1. If you look at just this part of the configuration, if we count up the top numbers as 2, 4, and 10, and if you go to the periodic table, number 10 on the periodic table is neon, which is the noble gas. And that's why we put it in brackets. So when we put it in brackets, it implies neon's electron configuration. And then we continue on with the rest of it, which is 3s1.
Now, why do we have to drop the 3s1 for?
Why do you ask you? I'm sorry.
Why do we have to drop the 3s1 if why are we dropping the 3s1 or the 3s1?
We need the 3s1 to get to 11.
Oh, okay, that's why. Okay, perfect.
Yeah. So what's in the brackets is
I
really,
see what's going on. Okay, yeah. So you're putting the
and that would be our 11th electron.
four. Okay, got it. That makes sense. Okay,
Yeah,
and
so
then
that's why it's sort of
last-
shorthand, so you don't have to write out all this. And
Now,
then-
is it always the last one though?
So when you look at the periodic table, like over here, group 8 is our noble gases. So what goes in the bracket is always the noble gas that comes right before your element. So, if your element was here, you would go back to the noble gas that came right before it. If your element was here, you would come back to the noble gas that comes right before it. So it's always the noble gas group 8, and it's always the one that comes right before where you're writing your electron configuration for.
So when you drop it down, that it adds. Okay, got it. Okay, perfect. Thank you.
You're welcome. Other questions?
Yeah, Professor Ifan, another question. Okay, so this. I notice you put 1s squared, 2s squared, 2p, and then you use a 3s1. Okay, on the chart. Let's see, hold on. Let me look at the NE. Okay, NE is 10, right? You use 3s. For the 3s, from 1s squared and then 2p.
Okay. I'm sorry,
Okay.
I think I might have missed your question. What was your question about?
Yeah, no, still getting together. Hold on.
Okay, so if you want, why don't you?
Okay.
Yeah.
Yeah, you know what? Never mind. I got it.
Okay.
Thank you.
Yep. And to answer your question that was in the chat box, if you need a periodic table, it'd be provided for you. I don't actually think you need one for this quiz. Okay, so that's electron configuration there.
Professor, I have a quick question.
Yes, sir.
Regarding, how you did the neon plus the 3s1, I think on the last one. Does that only apply for neon, or could you use it for other elements as well?
You do all the noble gases.
All the noble gases?
All the noble gases. So for example, here's potassium. And if we do this part of potassium's configuration and count up the top, that's 2, 4, 10, 12, 18. And again, if you go to number 18 on the periodic table, that is argon. So that's why on this one, we could shorthand it by taking argon, which would imply that part of the configuration, and then continue on for our potassium. So it doesn't always have to be neon, but it is always the noble gas that comes right before the element you are writing the electron configuration for.
Okay. All right. Thank you.
You're welcome. Okay, so when we talk about electron configuration, obviously you need to be able to write it. And again, if you recreate that order, it's really an easy way. You could actually use the periodic table if you wanted to count off electron configuration. The first two groups are what are referred to as the S block. S has 2 electrons. That'll be 1 electron, 2 electron. Groups 3 through 8 is the P block on the periodic table, and that has 6 electrons. So 1, 2, 3, 4, 5, 6. The transition metals is the D block on the periodic table, and that has 10 electrons. So if you just count off the squares basically. And down on the bottom is the F block, which has 14 electrons, which again, if you count out all the way across, you have 14. There are period numbers. So it's like period 1, 2, 3, 4, 5, 6, and 7. And again, so for example, you know, if we were going to do something like sodium, which is kind of like right here, right there, this would be 1s2 to there. This would be 2s2 to there. This would be 2p6 to the end there. That would take us to neon, right? If you're looking at a periodic table, we're at neon. And then one more here would be 3s1. So you literally could count off the electron configuration from the periodic table. But you do need to know what you're doing. I wouldn't recommend doing it this way. I would recommend doing it with the, you know, the thing that we made and the kind of the arrows. That's because right here, that is actually 3D, even though it's on period 4. So it's actually 1 behind the period number. That'd be like 3D, 4D, you know, 5D, you know, 6D coming down. And over here, this is F. This would be 4F, which really goes into here. And that's 2 behind. So there are a couple of places, if you don't really know what you're doing, you might not count off the electron configuration right. But you can use it maybe to sort of check yourself along the way. But again, you usually will never go wrong if you use kind of the thing we were using, where you kind of zigzag back and forth. All right, so we talked about that. Any questions on electron configuration or how to write electron configuration? So let's talk a little bit about electron configuration and some different types of electrons. First off, there are what are referred to as valence electrons. Valence electrons are the outermost electrons, the one in the highest energy level. And if we look at the electron configuration for nitrogen, 1s2, 2s2, 2p3, nitrogen is number 7 on the periodic table, means it has 7 electrons. When we look at this, there's actually 2 electrons here on the first energy level. Remember that first energy level is actually the lowest in energy. And then there's also on the second energy level here, there are 2 electrons and 3 electrons, which is 5 electrons on the second energy level. Remember that the number that comes in front is basically the energy level. So 2 is higher than 1. And the ones on the highest energy level are what are referred to as being valence electrons. So something like nitrogen would have 5 valence electrons. The electrons that are not valence electrons, that are lower in energy, closer to the nucleus, these are what are sometimes referred to as core electrons. For the most part, in bonding and everything, it's all about those valence electrons since they are the highest in energy and furthest away. Now, you absolutely could write the electron configuration for everybody to figure these things out. For example, we just looked at sodium, which was 1s2, 2s2, 2p6, 3s1. Here, 3 is the highest number, which means that sodium here would have 1 valence electron. The rest of these here would be our core electrons. Now, when we write electron configuration to figure out valence electrons, we absolutely could do that. But there's a much easier way, and the much easier way is that the number of valence electrons actually equals the group number. So that is a much, much easier way and quicker way, obviously, to figure out the valence electrons. So the number of valence electrons equals the group number. And so, for example, group 1, where we do find sodium, has 1 valence electron. Group 5, where we find nitrogen, has 5 valence electrons. If we look at chlorine, which is in group 7, it will have 7 valence electrons. So if you need to know how many valence electrons there are, it does equal the group number. And that's obviously important for bonding, which we're going to talk about next. But again, you could write out the electron configuration and take those ones that are in the highest energy level. I will say there, one sort of thing that's a little bit different is the transition metals. And if you remember, if we did our transition metals, we go 4s2, 3d5, for example, and the rest of it there, which would be argon, 4s2, 3d5. And the s electrons or the s orbitals are lower in energy. So you get the electrons first, followed by the d. But what ends up happening for transition metals and only transition metals, there's actually a switch in energy that occurs once you start putting electrons into the d orbitals. And what ends up happening for transition metals is when the electrons go in, as I drew a second ago, they do go into the s first and then the d. But once you start putting electrons into the d orbitals, there's actually a switch that occurs, and the 4s actually ends up being higher than the 3d. And for transition metals, what that means is they typically will lose their s electrons first. So unlike sort of a representative element like sodium, where we just saw 1s2, 2s2, 2p6, 3s1. And if sodium loses an electron, it will lose those guys first to become sodium with a positive charge, which has only 10 electrons, 1s2, 2s2, 2p6. Now, if you took something, say, like whatever I have there, which is, we'll do iron, for example. Iron with no charge would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. In this case, should be 26, I think. So what ends up happening when iron, for example, loses 2 electrons and becomes positively charged, even though the 3d6 is at the end, because this is a transition metal, it will actually lose these electrons first. And that always happens for transition metals. And the correct configuration for this guy would end up being, I'm just going to shorthand it here, argon, which would be this part of the configuration, and 3d6. Then if it needed more electrons to lose, so for example, let's say iron had a +3 charge, it would lose these 2 electrons first, and then it would lose 1 electron there for 3 electrons that would be lost, and you would end up with argon 3d5. So what I'm trying to say, I guess, in terms of transition metals is they do behave a little bit different than regular metals, the representative metals like in group 1, group 2, or group 3. And they typically will have those 2 s electrons sort of considered as their valence electrons, but sometimes people will consider they could have upwards of 12 because they still do have the d orbitals as well. So transition metals are a little bit different than regular guys, especially when they sort of start losing electrons. When something that's representative like sodium, for example, loses an electron, it ends up with 10 electrons, which is the same electron configuration as neon. And that is really, as we'll talk about in bonding, really the whole purpose of bonding is for everybody to end up with the same electron configuration as a noble gas. And really 2 things that have the same electron configuration are what are known as isoelectronic with each other. So isoelectronic, so for example, the sodium with a +1 charge and neon with no charge, they are isoelectronic with each other because they both contain the exact same number of electrons. They both have the same number of electrons. So the easy way, the good news is in terms of valence electrons and sort of bonding and when we do drawing and all that, we really don't deal too much with transition metals. We just deal with kind of our representative guys on the outside. And that is very easily found by taking the group number, and that will give you the number of valence electrons. So we're going to finish up talking here in this sort of chapter about some periodic trends and, where we find, sort of the most reactive metals and most reactive nonmetals. Metals and nonmetals, in terms of the periodic table, there are a couple of important sort of trends. First off, one is size. So size decreases as you go this way on the periodic table, and it increases as you go to the left and down on the periodic table. And when we talk about really most reactive metals and nonmetals, the most reactive metals are found bottom left of the periodic table. Most reactive nonmetal found upper right of the periodic table. And the reason for that is they have a lot of differences when we think about some periodic properties. So let's talk about some of these here. First off, there's what is referred to as ionization energy. And ionization energy is the energy that's required to remove an electron from an atom. When we remove an electron, it becomes positively charged and becomes a cation, basically. And as you go to up and right on the periodic table, the ionization energy increases. As you go down and left on the periodic table, it decreases. That means up and to the right, it takes a lot of energy to remove electrons. Typically doesn't happen. Left and down doesn't take a lot of energy to remove electrons, and that does typically happen. So ionization energy to remove an electron. Metals typically have very low ionization energy. Non-metals have very high ionization energy. And here's a trend. There's our atomic size. And let's add a few things to this here to explain why we see very active metals and non-metals in certain locations. So as I mentioned before, size decreases to the right. As we go to the right here, again, our ionization energy increases. And again, coming down, it decreases. Our something known as electron affinity. Electron affinity is basically the energy change that occurs when an atom gains an electron. And electron affinity increases this way. And it decreases coming this way. Another really important thing is something that sometimes is confused with that, and that is what is known as electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. And that also increases as we go this way. Actually, fluorine right there is the most electronegative. And coming down, it decreases. So these are all what are referred to as periodic trends, and really why we see certain things occur. For example, if we go up and to the right on the periodic table, we have things that are very small, which means even the outer electrons are closer to the nucleus and held tighter. A reminder that the nucleus is positively charged, electrons are negatively charged. So there is going to be some attraction between those two. So as we go to the right, everybody is closer to the nucleus. It has very high ionization energy, which means it takes a lot of energy to remove electrons. It also has a very high electron affinity, which means it likes to hang on to its electrons and gain electrons. And it has a high electronegativity, which means it likes electrons to come towards itself. All of those periodic trends is what we know happens with nonmetals. And that is nonmetals typically will gain electrons and become negatively charged because they hang on to their electrons. Not only that, they bring electrons towards themselves, and it takes a very lot of energy to try to remove those electrons. Opposite is true if we go to the left and down on the periodic table. We have things in the left-hand side, bottom left, that are much larger in size, which means the outer electrons are further away from the nucleus, not being held as tightly. They have very low ionization energy, which means it doesn't take a lot of convincing to allow an electron to leave. They have very low electron affinity, which means they're not interested in gaining electrons. And they have very low electronegativity, which means they're not very interested in bringing electrons towards themselves. So that all goes really well with what we know for metals, which is they typically will lose electrons and become positively charged, or a cation, while again, our nonmetals there will become negatively charged, or an anion. So because of these trends, what we typically see is up and to the right on the periodic table, when we hit the nonmetals, those are typically our guys who are going to hang on to the electrons, gain electrons, and kind of to the left where we have our metals, those are guys, because of these periodic trends, typically will lose their electrons, not really hang on to their electrons, and become positively charged. Any questions on those trends there? Okay. So one way that we represent sort of bonding, and we'll see more of this in the next chapter as well, is through what is sometimes referred to as Lewis dot symbols or electron dot symbols. They're kind of generically called. So sometimes people just generically call this guy an electron dot symbol. I remember how to spell electron dot symbol. And because bonding only involves valence electrons, we only show valence electrons. And basically when we do Lewis dot symbols or electron dot symbols, we use the symbol for the element and basically 2 dots per side max. And each dot represents a valence electron. So for example, if we did sodium, which we just talked about is group 1, means it has 1 valence electron, we would write basically the Lewis dot symbol for sodium like that. If we did calcium, which is group 2, has 2 valence electrons, calcium would be something like that. And so forth, all the way through to say chlorine, which is group 7. It would have 7 valence electrons. We would draw chlorine and lay up 7 dots. Is there any rule as to how you do this? Not really. Most people kind of go around and then go back and pair up. The only real rule is no more than 2 per side. That maxes out at 8 electrons, which is a very important number in bonding, as we will talk about, but really no real rule other than don't put more than 2 dots per side. Any questions on that? That's what it says. So here's some examples of some Lewis dot symbols or electron dot symbols. Again, you can see everybody in group 1 has 1, everybody in group 2, 2, 3, 4, 5, 6, 7, 8. The one exception in group 8 is helium. Helium's electron configuration is 1s2, which means helium only has a total of 2 electrons, which means it can't have 8. But everybody after that will have 8. And here's all of our noble gases. They are perfectly happy because they have 8 electrons. And as we talked about with like sodium and so forth, when it loses an electron, it ends up back at argon. And again, that's the basis of bonding, is to get to the same electron configuration as those noble gases. We don't really deal too much at all with transition metals in terms of bonding or Lewis dot symbols. Again, this is what I was talking about earlier in terms of electron configuration. This would be like 1s2, 2s2, 2p6 here, and again 3s1, 3s2, 3p6 if you're counting electron configuration, 4s2, and this would be 3d1, and again that would be 5d and so forth. But you don't have to worry too much about these guys in terms of valence electrons and stuff like that. But again, sometimes people will say they have two, which would be these electrons here. Sometimes people will say they could have upwards of 12 because you could also use those d electrons as well. Any questions on any of that there?
Professor Stefan,
Yes, sir.
I'm noticing that on all the on columns, all the columns, when you place the dots, are they supposed to go in a specific order? Because I know you said randomly, but like I see like oxygen, it has 2 on top, 2 on the bottom, 1 on each side. Is that the way it has to be, or could it be
Yeah.
2, 2, and 2?
Truthfully, you know, unless you find somebody that's super picky, there's really no rule. The only real rule is you can't put more than 2 per side.
Okay.
So yeah. So for example, I just happen to do, sometimes people kind of go around and then pair them back up, but
Yes.
something like carbon here, you know, it's, in my opinion, it's not technically wrong if you just drew it like this, right? It has 4, you know, but
Okay.
most of the time people will kind of separate them out. But again, as long as you don't go more than 2, that's usually kind of the main rule on these.
Okay.
Other questions? Okay, that then wraps up the chapter there we were doing, which I think is 4. We are going to skip chapter 5 because I believe it's nuclear chemistry. So we're not going to talk about that chapter at all. So then we are off to chapter 6 after that. And 6 is going to kind of tie together all this stuff we've been talking about, electron configuration and sort of these valence electrons and these periodic trends. We're going to talk about chemical bonding. So we're going to talk about chemical bonding in here. We're also going to talk about nomenclature, how to name things. So we'll get started on some of this here. Okay. So we're going to start first off with the naming part of it and how to name everything. So first off, though, there are certain rules in terms of how you name things, but there are certain things that really do have common names that people kind of always use when they are talking about something. First one is H2O. H2O is water. It is not a trick question. If you see it, you should just write water. It is not dihydrogen monoxide because nobody wants a refreshing glass of dihydrogen monoxide. So write water. NH3 is ammonia. CH4 is methane, and that is the simplest organic molecule you could have. The rest of these two here, I'll be honest with you, most people will call this sodium chloride, and that's table sugar or sucrose. But I would say for us, these first 3 for sure, you should definitely know the common names. We're now going to talk about really sort of the other way of naming. So these guys, the more non-common way, I guess, is the way of doing that. So first off, let's talk about the 2 types of sort of compounds we're going to name. And they're sometimes referred to as binary compounds, which means they're basically made up of 2 elements. And one contains a metal and a non-metal. And this type of situation is what is referred to as an ionic bond. And in an ionic bond, as we will talk about, there is a transfer of electrons from the metal to the non-metal. And what ends up happening is the metal becomes positively charged, or a cation. The non-metal gains the electron, becomes negatively charged, or an anion. And these 2 guys are held together by what's referred to as electrostatic attraction. And that basically means opposites attract, positive, negative attraction. There's absolutely no sharing of electrons here. And that is different than compounds that contain 2 nonmetals. When we have 2 nonmetals, this is what is referred to as a covalent bond. And different than an ionic bond is it's actually sharing of electrons here. And those electrons may be shared equally or unequally. And we'll talk about that obviously in this chapter as well. But there's some aspect of sharing of electrons, which essentially holds that thing together. So we're going to focus in here first off on ionic compounds, which contains a positive and negative guy. And so we're going to start with ionic compounds, which again is always a metal and non-metal. And pretty much if you could identify it as a metal and non-metal, you could not go wrong by calling it ionic for sure. So let's just start with basic periodic table. I think we talked about, but just in case we didn't, let's make sure. When you go to periodic table, there are certain things or groups that have sort of a fixed type of charge. So if we look at our different groups here, now everybody in group 1, because of all those periodic trends, pretty much will give up their electrons and become +1 charge. By the way, things do not have a charge until they hook up with like a metal and non-metal. So if you have like a piece of copper metal by itself, it does not have a charge. It will only gain a charge if it hooks up with a non-metal. Group 2, everybody there will always make a +2 charge. Group 3, pretty much aluminum we're talking about here, will make a +3 charge. And if you look on the periodic table, right above aluminum is like boron. There's that staircase that we talked about that comes down. And talking about our non-metals up on top, we skip group 4. Going backwards, group 3 will make a -3 charge, -2 charge, and -1 charge. And again, these are our non-metals we're talking about above the staircase. And these guys are our metals. And that means something like sodium, which is group 1, will always, when it makes a charge, will always be +1, no matter what the situation is. You'll never find a sodium that has a +2 charge or +3 charge. It always is going to be +1. Just like calcium, which is group 2, will always be +2. You will never find a calcium, with a +3 charge, +9 charge or anything like that. It will always be a +2 charge. Now, this is our transition metals in the middle. And these guys have a variable charge, which means some of them can be, for example, copper, which is a transition metal. In certain cases, could be +1. In certain cases, copper could be +2. But there are 3 sort of transition metals that do have fixed charges. Zinc and cadmium will always make a +2 charge. And if you hang a left over there to silver, it will always make a +1 charge. So that backwards L, even though it's a transition metal, will have basically fixed charges. So these are important to remember as we go through sort of our naming and our process here, these type of charges. And again, these guys only really do gain these charges when they start to interact with like a non-metal. Any questions on that? So ionic compounds are made up of ions, and ions are things that have charges. And obviously there are cations, which are positively charged. And these guys are a result of losing electrons. Basically, you have more protons than electrons, so you become positively charged. So how do we go about naming these guys? So if we had something like Na+, Ca2+, Al3+, maybe even H+. When you have just a cation by itself, these are the formulas for the cations. When I write it, a cation by itself, the charges do need to be included. Again, for a cation, because it's an ion, you just include charges. But to name cations, you simply just use the whole name of it. So this would be sodium, and then you just put ion at the end. Ca2+ would be calcium ion. Al would be aluminum. This would be the aluminum ion. H+ is hydrogen. This would be the hydrogen ion. So the way we go about naming things that are positively charged, that are cations, pretty simple. You just simply use the entire name of the element. And again, if you were asked to write the formula for the cation, this is what it should look like. Again, should have the charge included on those guys. So what happens when we have somebody that is negatively charged, are an anion? And those come from our nonmetals. And those are negatively charged guys. And that is from gaining electrons. They are named kind of the same way. We use the root of the name, of the nonmetal name, but they get IDE at the end of it. So we drop the last part of the name and put IDE. So for example, oxygen, which is group 6, has a -2 charge. So we drop the last part of oxygen and put IDE in there. And this is the oxide ion. If we look at Cl minus, that is group 7, -1 charge right here. That is chlorine. We drop the last part of chlorine and we put IDE at the end of it, and it becomes a chloride ion. Hydrogen is an interesting one. It is one of the only ones that actually could go both ways. It could be positive like we see on the bottom here, but hydrogen actually can be negative as well. And you can have H minus, and that happens when it comes after a metal. And it's named the same way. We drop the last part of hydrogen and we put IDE at the end of it, and it becomes the hydride ion. So one important sort of naming process is if you have a cation which is positively charged, you simply just use the entire name of the element. So that's pretty straightforward. If you have a nonmetal that is negatively charged, or an anion, we basically use kind of the front part of the nonmetal name and we add IDE at the end of it. Any questions on that there? All right, so I think what we're going to do is we're going to lay it up there, since you do have a